All right, today we're going to walk through a field investigation of a failed industrial gearbox. The whole point here is to look at the physical evidence, the damaged parts, and work backwards to find the root cause.
At its core, an industrial gearbox has one job. It takes power from a motor and reliably transmits it as torque and rotary motion to whatever piece of equipment it's driving. Simple as that.
But when it fails, everything stops. The whole process goes down. Production is lost. So understanding why these things fail isn't just a technical exercise. It's absolutely critical to keeping a plant online and running.
So where do we start? The investigation always begins with a call from operations reporting a problem out in the field. That's our trigger.
The call usually sounds something like this. We've got high vibration, or there's a new strange noise, or the unit is running way too hot. These are the classic symptoms, the first signs that something inside is starting to go wrong.
Okay, before you shut anything down, there are a few checks you have to make. First, look at the motor amps. Is the drive overloaded? Pull an oil sample right away. We need to see if there's any metal or other contaminants in there. If you can, get a temperature reading on the bearings. And really listen to that noise. Is it a rhythmic knock, or is it a continuous grinding? Each one of these is a clue that helps us figure out what's happening inside.
Once the unit is safely shut down, locked out, and the inspection cover is off, the internal investigation begins. We'll start by looking for the most common type of gear failure, which is surface fatigue.
Pitting is the textbook example of surface fatigue. It's caused by the repeated high-contact stresses right where the gear teeth mesh, what we call Hertzian stress. When those stresses are higher than the material's fatigue limit, cycle after cycle, they create tiny microcracks. Eventually, a small piece of the surface breaks away, and that leaves behind the pit you can see.
Now, it's really important to know there are two types of pitting. On the left, that's what we call initial or corrective pitting. This can be normal during the run-in period, as high spots on the teeth wear down and conform. It should stop on its own. What you see on the right, though, is destructive pitting. This doesn't stop. It gets progressively worse, and it's a huge red flag that you have a fundamental problem, most likely an overload condition.
If you get a good look at a classic fatigue pit, it often has this distinct arrowhead shape. And that's a useful clue, because the point of the arrow actually tells you the direction of the rolling contact across the tooth surface. You'll find that destructive pitting almost always gets its start in the dedendum. That's the part of the tooth below the pitch line. The reason is simple. That's the area that sees the highest combination of rolling and sliding forces, which makes it the most vulnerable part of the gear. Spalling is what happens when pitting gets much, much worse. This is an advanced stage of fatigue. You're not looking at individual pits anymore. Instead, you have large areas of the surface material that have completely broken away. The damage has escalated significantly.
This is a very clear example of spalling on a surface-hardened gear. You can see these large, fractured zones where the hardened case itself has failed and broken off. This isn't just a bunch of small pits that have grown together. It's a catastrophic loss of the wear surface, driven by extreme stress or a flaw just below the surface.
The second major failure category we look for is wear. Now, unlike fatigue, which is about cracking, wear is the physical removal, the loss of material from the gear tooth surfaces.
We see two primary types of wear. First is abrasive wear. This is pretty straightforward. You have hard particles like dirt or metal debris in the lubricant, and they act like sandpaper, grinding away at the surfaces. It leaves behind scratches or a dull matte finish. The other type is adhesive wear, often called scuffing. This happens when the oil film breaks down and you get direct metal-to-metal contact. On a microscopic level, the surfaces weld together and are instantly torn apart, which rips material from the tooth. This leaves a very different appearance, a burnished or scored look.
Here's a textbook example of abrasive wear. What happened in this case was a bearing started to fail, releasing hard steel particles into the oil. The lubrication system then circulated that contaminated oil right through the gear mesh, effectively lapping down the gear teeth. So here, the gear failure was actually a secondary failure, caused by the bearing.
Okay, so once we've identified the evidence on the gear teeth, the next step is to connect that specific failure mode to its probable root cause.
This table really pulls it all together. If you see destructive pitting down in the dedendum, your number one suspect has to be system overload or shock loads. The next action is to compare the gearbox's original service factor against the actual loads. If you see abrasive wear that causes contamination, the next step is to analyze that oil sample to find out what the contaminant is and where it came from. And for adhesive wear or scuffing, the problem is inadequate lubrication.
You need to verify that you're using the right oil, the right viscosity, and that your operating temperature is where it should be.
And when we talk about overload, it isn't always a steady-state problem. This torque reading from a steel mill drive is a perfect example. The average running torque is fairly low and consistent. But look at those spikes. Momentary peak loads that are 7 times higher. That is a severe shock load.
Now here's the crucial part. A standard motor ammeter will never register these brief, transient peaks. They happen too fast. But the gears feel every bit of that peak load, and it's those high-energy spikes that are the real killers when it comes to fatigue failures. To do a proper analysis, you have to understand the peak load, not just the average.
Once the root cause is confirmed, the final and most important step is to implement corrective actions to make sure this failure doesn't happen again.
So first, you have to verify the sizing. Is the service factor of that gearbox actually appropriate for the real-world load profile, including those transients? Second, you have to improve your lubrication practices. That means clean handling, proper filtration, and a routine oil analysis program. Third, if shock loads are the problem, you need to see if you can mitigate them in the process upstream. If not, maybe you need a resilient or torque-limiting coupling to protect the gearbox. And finally, always check the alignment. Misalignment from the couplings puts bending loads on the shafts that will take out bearings and gears.
Every failed component leaves behind clear evidence. The gears, the oil, they tell the story of exactly what went wrong. A careful, methodical inspection is what gives you the data you need to solve the problem for good. So, what are your gearboxes telling you?